Hello, everyone. In this paper, we proposed a method, multi-source collaborative gradient discrepancy minimization, for federated domain generalization. The deep learning has made a great progress by assuming that the training data and testing data from the independent and identically distribution, when the source domains and target domain exist domain shift, as shown in Figure 1, the performance on target domain will degrade largely. Furthermore, the data from different domains keep decentralized data privacy restrictions, which brings the difficulty for bridging the domain gap. In this paper, we aim to solve the multi-source domain generalization problem under the data decentralization scenario, as shown in Figure 4. Domain generalization assumes that the data from multiple source domains can be accessed simultaneously to learn a generalizable model for deployment on the unseen domain. Federated domain generalization assumes that the data from different source domains are decentralized, but the local models of different domains can be collaborative and aggregated with a parameter server. Federated domain adaptation assumes that an additional unlabeled target domain can be accessed on server side for improving the performance. In this paper, we focus on the federated domain generalization task, and our method can be extended to federated domain adaptation. The motivations of our method are follows. 1. Collaborative train the decentralized domains. Due to the data from different domains are decentralized, we utilize the federated learning framework, e.g., FedApp to collaborative train the multiple decentralized source domains. 2. Gradient discrepancy indicates the domain's formation, inspired by the hypothesis that the gradient discrepancy between domains indicates the model updating to be domain-specific. We utilize the gradient discrepancy to detect the domain shift. 3. Reducing the domain shift under the data decentralization scenario. Under the data decentralization scenario, we propose to learn the intrinsic information within isolated domain and reduce the domain shift between decentralized domains by reducing the gradient discrepancy within domain and across domain. The overall framework and contributions of our method are shown in Figure 4. Framework. There are 4 steps in each round. Step 1. Local training on source domains. Step 2. Upload the local source domain models to target domain. Step 3. Model aggregation on server side. Step 4. Download model to source domains for the next round training. Contributions. 1. We propose intra-domain gradient matching within isolated domain to learn the intrinsic semantic information across original data and the augmented data. 2. We propose inter-domain gradient matching between domains to reduce the domain shift by utilizing the classifier heads of other domains. The loss for training the local models is shown in Equation 1, where LCE is the cross-entropy loss on labeled source domain. X is the data augmentation function, e.g., randog. L inter-GM and L inter-GM are the intra-domain and inter-domain gradient matching loss respectively. Lambda is the hyperparameter. Conduct intra-domain gradient matching and inter-domain gradient matching for reducing the domain shift and improving the generalization of model. Under the data decentralization scenario, on the server side, we average the local source domain models by parameter averaging, as shown in Equation 4. After model aggregation, the global model is broadcasted to source domains for the next round training. Our method can be extended to the federated multi-source domain adaptation task when the additional unlabeled target domain exists. Following previous work, e.g., KD3A, we train the target domain model by pseudo-labeled target domain data, as shown in Equation 5. Then the model can adapt to the target domain. Compared with the state-of-the-art methods, our method can achieve the significant performance improving on federated domain generalization task and federated domain adaptation task. We also conduct ablation studies to validate the effectiveness of each components, compare with other alignment strategies, and combine with other data augmentation strategy. Furthermore, we conduct data visualization by GradCam to validate the effectiveness of our. In this paper, we propose a multi-source collaborative gradient discrepancy minimization method for federated domain generalization, and the extensive experiments on federated domain generalization and adaptation datasets can validate the effectiveness of our. Thanks.